we're looking at mechanics today. So yesterday was sort of the overview, trying to get the big picture of how the course is structured, put together, or the different subdivisions within it. And we'll return to that in the last session, which is midweek next week, to talk about exactly like how you would plan out in detail your study, your revision between now and, well, now and the end of June, well, now in June, I should say. And also, of course, there's another deadline this year, which is really the middle of May, in that we really have a sort of a double deadline, in that you will be assessed, obviously, in June. And I imagine most people who have signed up for this are looking at doing the exam. But realistically, I would imagine, again, most of you will also be getting a calculated grade or estimated grade from your teachers, and that may involve some tests and, well, assessments, tests, whatever we call them, over the 6-7 weeks when we get back to school. So you need to be tactical about this and clever about it, and everybody's going to be in a slightly different situation, but we'll sort of try to get an overview of all of that when we've worked our way through all the course material at the end, and just talk about like the best ways you could maybe approach your study and your planning over the whole time between now and the summer. So today we're going to be looking at all the material and mechanics, focusing essentially on the section B material, the questions that come up in section B. We looked yesterday at section A, the experiments, and really it's all maths, method and accuracy there. So review all the experiments, and I wouldn't cut any corners there, no matter what other corners you might cut. Don't cut them in the experimental area, because it's the possibility of hitting the top grade in the experiments is really there for the taking. But any corners that you cut, there's a risk of it biting back and costing you marks on the day. And it really comes down, for each of the 24 experiments, make sure you know the maths, what graph, what formula. The method, can you draw the diagram and briefly outline how the experiment was done? And are you aware of one or two issues that tend to undermine the accuracy of the experiment? If you do that and look through past papers, you will find that that they find slightly different language every time, but basically that's what they're looking for in every single question in section A, going back over 20 years now. Tomorrow, we're going to look at the whole area of light, sound and waves basically. And within our study of waves, we look more specifically at light and sound. That includes optics, Doppler effect, Young's experiment, all of that. It's actually a huge section. It's the one where we'll, along with electricity, where we'll have to cherry pick the material we look at more than in any other parts of the course. The mechanics, obviously we're not going into immense detail here, but there'll be very little, subject titles within the mechanics that we won't have addressed even briefly between yesterday or today. Whereas light, sound and waves, there are a few bits that you have to skip across in short sessions like this. And then next week we're going to look at modern physics, electricity, and then sort of mop things up on the last day, a little bit of heat, a little bit on the particle physics option, and sort of how you might study, how you might plan and organize yourself. But the main thing, you're obviously doing these sessions anyway. The main message is that let past papers guide your work at this stage. Don't feel that you should be using the exam papers as a way of testing yourself. That'll come, but that's the last few days. For the moment, use the exam papers as a guide to what's important and the depth of understanding that's expected of you coming into this test in May or June. Now, a few websites that we'll be dipping in and out of over the next few classes that I think a lot of teachers use these, but I don't know if it's a safe assumption that everyone does, and they're openly available. So if you haven't seen them, you should check them out yourself. They can really help getting the basic concepts clear in your head. PhET is one. You can see there's a long address there, but really if you Google PhET, excuse me, it's the first link that will come up, and they have loads of great interactive simulations of pretty much all the core concepts relating to physics at this level and a bit beyond this level, as well as some relating to chemistry, biology and maths. Another one, the graphics are a little less impressive, but The way it animates the physics is maybe even slightly better, is Walter Fent. And that's a .de address, but he has loads of different addresses. Again, if you just Google the guy's name, Walter Fent is F-E-N-D-T. And always worth checking out the Institute of Physics website. It's aimed mainly at teachers rather than students, but you might well find stuff there that helps you, particularly if there's any concept that you're really struggling to get your head around. Very often when you're struggling to get your head around a topic in physics, it's not because it's particularly difficult. It's very often because it's an interactive, changing kinetic situation where things are changing as time passes. And if you're trying to learn that from a book and diagrams where clearly nothing changes, it's an artificially difficult scenario. So always, if you find yourself just struggling with what a basic concept is, tap it into Google, see if you can find any animations that just might make it more obvious to you. Now, the mechanics, these are the subsections within it: conservation of energy, vectors, Newton's laws of motion and gravity, circular motion, satellites, simple harmonic motion. They're all the big topics. There's a little bit about pressure, buzz, that we saw a tiny bit about yesterday, and moments as well that I won't be getting a look at today. This is the weighting of the different topics. And I say, and obviously, like we were talking about yesterday, it's hard to know exactly how that might vary this year, particularly in section B, where in section A there's sort of an obvious pattern that they'll bring up: one question from light, one from sound, one from mechanics, one heat, and one from electricity. That it's a guess, but it's like, I'd be really surprised if that isn't the case. Whereas in section B, it's a lot more unwieldy. There's a lot more variation from one year to the next. So I don't think we can predict too clearly there how it might vary this year compared to the past. But in the past, mechanics has always been very predictable. It's always been question 1, 6, and 12 part A. So it's one question in A and 1.5 in section B, which is 2.5 questions. And the weighting, I don't think is going to change. Where those questions turn up probably will change this year, but it's going to be similar or slightly more questions. So even if we stick to the past pattern, in the past, your question 1 would be worth 10%, question 6, 14, and question 12 part A would be 7%. So the mechanics in the past would be worth 31% if you focused on this material. This year, even if they don't bring up any extra questions on mechanics, just on those same number of questions, it would end up being worth 40% because of the different weighting between section A and section B. So, I mean, just focusing on this material can have a huge influence on your grade. And of course, some students yesterday, when we polled, are saying they're not aiming for 70 or 80 or 90%. I just don't want to put words in your mouth, but basically trying to get out of trouble here. Like, experiments and mechanics alone could get you out of trouble, though I'm not recommending it. But be aware, particularly if you are looking at those top grades, that if you were to rely and say, okay, I'm going to do the mechanics and I'm going to know the electricity, the risk is that when you go into the exam, you'll find a lovely question of mechanics and you're good for 45 out of 56 marks, but the other 11 marks might relate to something in electricity or heat or optics. They really love mingling topics together. And they've done that increasingly in recent years, and I'd be surprised if there isn't a serious amount of that this year as well. Now, key definitions amount to 17, maybe 18, 19% this year. That's a list of the likely definitions, like demonstration experiments. There is no clearly defined list of definitions that we can give you and say, if you learn these, you're guaranteed to get your marks 100%. It's largely left up to the judgment of teachers, students, to decide which definitions to be ready for. But I mean, that is the common sense list, and it will cover you, not more than 9 times out of 10. And this is all in the notes, and I was referring to the notes yesterday. I didn't show them to you. I will flick through them today, and I'm just making a few changes to make sure they're all ready to go out to you at the end of this week's sessions. Now, the mechanics is the most mathematical part of the syllabus. And you need to be very familiar with your maths tables to max out your score here, where the mechanics formulae begin on page 50 of your tables and go up as far as 57. So that's 8 pages of formulae relating to mechanics. And the risk with that is that if you're not familiar with the tables in advance, you might find yourself flicking through it desperately, knowing there's a formula in there, but not able to find it. So as much as possible over the next few weeks or months, don't be using the textbooks or notes or whatever you have to find formulae when you're trying to figure out questions. Try to do it using the tools you have in the exam, the maths tables. But a few key formulae that you're going to be using over and over again that are very likely to feature in any exam: kinetic energy, energy due to motion, which follows the formula half mv squared. M is mass, v is velocity. And potential energy. Now, potential energy has many forms, like electrical energy. Voltage is a measurement of potential energy of a sort, electrical potential energy. That's why we talk about potential difference. If you pull back an elastic band and then let go, that's, it moves. It was storing up energy in its shape due to relating to Hooke's law. And they're all forms of potential energy, but the main one that you're likely to have to calculate in the test is the energy you give an object by lifting it up, gravitational potential energy, and that follows the formula mgh. Again, these are all in your tables, but realistically, it's not that you have to learn them off by heart. There's no harm to look them up if you need to, just reassure yourself, but you should be practicing with these enough that they're, almost second nature to you before we get anywhere near the summer. Now, they're likely to come up linked in with the equations of motion, often called the U-VAST equations, where U always stands for initial velocity, V for final velocity. That's for an object that's accelerating. A is the acceleration, S is displacement or distance traveled, and T is the time over which it has traveled. Now, we talked yesterday about how I'm not going to be getting into the dangerous game of telling you what's going to come up this year, making predictions, making guesses, and in particular, not playing the game that can absolutely obsess students. And I was the same. I'm not judging anyone for this, of excuse me, of looking for obscure patterns, almost as if there were secret codes that will let you know what's going to come up this year. And some of those, if you make those guesses, some of your guesses will be right, because guesses sometimes are right, but there are no obscure patterns. If the department spots one that has just happened naturally as stuff comes up every few years, they clearly and demonstrably set out to break those patterns just to make sure that we don't slip into trusting them. But the one pattern, or the type of pattern you should look for, is not the stuff that comes up every 2 years or 3 years or 4 years. Forget that. It's the stuff that comes up every year. And wave nature, for example, some variation on Young's experiments, that comes up virtually every single year. And the equations of motion, I'm pretty sure, have come up every single year that I've been looking at Leaving Cert Physics, stretching back into the 1990s. So that's a pattern you want. Equations of motion are coming up. You don't need any subtle hints or analysis to get there. Just observe the obvious. And remember, work from your tables here, page 50 to 57. Now let's jump straight into a question and look at how this might be asked and how all those topics can come up and how they tend to interlink them. So on a bungee jump, Henry falls while attached to an elastic cord. When the cord stops Henry's fall, he then oscillates up and down. During the bungee jump, gravitational potential energy is converted into kinetic energy and then into elastic potential energy. State the principle of conservation of energy, which that's the first part of the question, which should really be junior cert knowledge. States that the energy can neither be created or destroyed, but that it can be converted from one form into another. Derive the expression V squared equals U squared plus 2AS for uniform accelerated motion. Sorry, should have pointed out before. That definition will be worth 6 marks, which this year will be worth very slightly under, realistically 2%. It's like 1.9 something percent. Derive the expression v squared equals u squared plus 2as for uniform accelerated motion. So how do you get that derivation? Say there's not an infinite list. We talked about them yesterday. You start in this instance with v equals u plus at and you square both sides. Junior cert algebra type skills required, u plus at in a bracket. Multiply u plus at by u plus at, you get u squared plus 2u at plus a squared t squared. Then you factorize. Take 2a out of this, so 2a by ut gives you that first expression, and 2 by a half gives you 1. A by at squared gives you a squared t squared. Now, factorizing, taking a 2 out of an expression where there isn't a 2 there, leaving you with a half would be odd, but of course that bracket now can be replaced by s. S equals ut plus a half at squared. So v squared equals u squared plus 2as. 3 lines of algebra. Worth typically, when these come up, 12 marks, which would be 4%. So if you knew your definitions and your derivations, you'd already be on like 6% on this question. Your derivations, it's such a simple, it's a chore. No one likes learning derivations, but you know, if you can sit yourself down and discipline yourself to work your way through them, you know, I'd say if you've half learned them in the past, you're probably an hour from, you know, knowing them and be ready to trot them out in an exam. If you haven't, it might take 2 hours, but it's not a vast amount of material. If you survive junior cert maths, you can survive these derivations. Typically worth 3%, but I'd expect that to rise this year. And if 2 of them come up, like that 3 turns into 6, but this year that might be more like 8. Now, the cord is 32 meters long, and Henry of mass 60 kilos falls from rest while attached. Calculate his speed when he has fallen 16 meters for 21 marks. So one way of approaching this is that as he falls, he obviously gains speed. So the speed or kinetic energy gained will be equal to the potential energy lost. Your kinetic energy is coming from your potential energy. So turn to your tables, look up those formula that we've just looked at, and the kinetic energy that we're looking to calculate must come from potential energy, mgh. The m's cancel, so in fact we know it, we need it later on in the question, but the m's cancel each other out, and v squared is 2gh. You know 2, you know g, it's given at the bottom of this question, 9.8, and h is 16 meters fallen, so v squared is 313, and v is 17.71 meters per second. Now, we'll come back and look a little later on about how that might have been marked. But another approach, now you don't need to do it both ways, but if you saw either approach, both would be valid. Another way of approaching that, forget about all of that, and look at it in terms of equations of motion. We're looking for the speed when he's fallen 16 meters. So we know u is 0. He's not falling when he steps off the platform. V is what we're looking for. Acceleration is 9.8. We're looking at a distance of 16 meters. So V squared is 313.6 and V again is 17.71. Now, what's important there, you could approach that from a conservation of energy perspective, potential energy lost equals kinetic energy gained, or you could approach it from an equations of motion perspective. Both are valid, both are fine, both will get you full marks, and both were hinted at earlier in the question. If you're stuck on a mathematical problem, you know, if there's numbers there, it's a mathematical problem. Glance back up to the beginning of the question. And here at the beginning of this question, we'd already been asked to derive the equation v squared equals u squared plus 2as. So it was always likely that that was going to crop up again during the question. Like, that's not coincidental. They designed these questions thematically so that these things happen. And if you didn't spot that, well, the first thing you were asked to do was conservation of energy. So it was always likely that the question was going to be based on conservation of energy. So if you're stuck, stumbling through it, not sure what to do, look up at the beginning of the question. Whatever was referenced there is likely to be what gives you structure to the rest of the question. Now, so equations of motion, kinetic energy, potential energy often come up. They're often interlinked, and they often interlink with Newton's laws, particularly Newton's laws of motion. Let's run through them very quickly. First law, a body will continue in a state of rest or uniform velocity unless an unbalanced external force acts upon it. Now, what Newton was pointing out here was two things. First of all, that if an object is sitting there, it's not going to move unless we make it move. It will continue in a state of rest unless an unbalanced external force acts upon it. But similarly, if something is moving, it won't stop unless a force makes it stop. Now, if you think of something, sliding along the floor or table or wherever you're working right now, what makes it stop is usually friction or some variation on friction, air resistance, water resistance, and other motion, but basically friction. And everybody knows this, a child knows this, they might know the word friction, but they get the idea that things will stop moving because as they slide across, one object slides across another, there's always a force that slows it down. So that, like, we know that from childhood. So the genius of what Newton put together here, and other people before, I mean, Newton brought it together and put the maths into it all, but other people had seen a lot of this as well, says that if friction is what stops something moving, in the absence of friction, stuff won't stop. It'll travel forever. Now, the fact that in our everyday experience, there's always friction shouldn't obscure from us the simple truth of that an object, once moving, will not stop unless a force comes along. And in space, and now not just in space travel with people, but in all of the work with satellites and unmanned spacecraft, that's key to it. That, like, when those spacecraft, when they get them away from Earth, when they have like Voyager, which has been traveling for 30-something years out into the vast void of space and is now outside the solar system, there's no engine driving that. They got it up to high speed and just let it loose, and it will continue traveling at that speed forever. And astronauts have to be very careful of this when they're working around space stations or space shuttles, that if they don't push away from it, because if they do, there's nothing to pull them back. There's no reason why they'll ever stop. They'll continue traveling forever. Second law of motion is in many ways the most important, but maybe the least interesting. It's what gives us the equation F equals ma. And that's what ties all his other ideas together mathematically. So by creating a way in which forces could be measured and related to accelerations and changes in motion, he allowed all his laws to be tested, to be tied in with gravitation, to be tied in with satellite motion. It's enormously important. And really, it's that law that made the Newton's laws. The other bits, other scientists of that time had sort of got their head around, but it was this way of mathematically analyzing them all that made it Newton's world. Third law, if body A exerts a force on body B, then body B would exert an equal but opposite force on body A, famously known by people outside the world of science as for every action there's an equal but opposite reaction, which was actually, he wrote it in Latin, but those were Newton's words, essentially. And the reason that they're not used in textbooks anymore is because the word action is a little obsolete. We use the word action all the time, of course, but in this exact context, what did Newton mean by action? He meant one body pushing against another body or pulling against another body. Two bodies had to interact for there to be what he called an action. So for the sake of clarity, we normally avoid that phrasing and go with body A and body B in modern textbooks and modern science. Again, space travel brings a lot of these to the fore of greater clarity. When a rocket blasts off, the fuels, as it expands when ignited, is pushed downwards by the rocket, and the equal but opposite force pushes the rocket up. That's why it works in space too. The rocket isn't pushing down against anything. It's what happens inside the rocket that matters. So up in space, in orbit, when you want to speed up, slow down, or change direction, they just put very small amounts of gas emitted. So the spacecraft pushes the gas out, and then the gas pushes the spacecraft forward or sideways, whatever they're trying to do. Now, here's a poll question coming up, if Fiona's there. Newton's third law of motion says that for every action, there's an equal and opposite reaction. So if you look at that, if I hold my pen above the world, so hold my pen, the action is that the Earth is pulled down, the pen is pulled down by the Earth. That's gravitation. What's the reaction? So have a go. Ignore question 2 here. Just have a go at question 1. Just pick. We don't see your names here. So we're not going to judge you.
Yeah, we can relaunch question 2 later on.
Yeah, we can just put it back up again. It's fine. 30 out of, oh, we got more people here than yesterday. So give it another 10 seconds. Just commit. What's the worst that can happen? Forcing yourself to commit can be a big part of learning, because whether you're right or wrong, it means you've engaged your thoughts. Okay. So let's leave it there, and we'll share results. So the pen falls to the earth, which seems to be the most popular option, just under half. The pen bounces off the earth. The earth is attracted to the pen, or there is no reaction. Well, I'm happy that we've got nobody going for there is no reaction, because the word law is a bit overused in science. It's a bit inappropriate the way we use the word law. In fact, it's more a relic of the past, because a lot of what we know as laws don't really work. Like Boyle's law only works for gases at low pressures. It's not much of a law if it only works in certain circumstances. Ohm's law only works for metals and only works if we maintain the temperature constantly. So if you have all these exceptions, what sort of law is it? But Newton's laws really are. They apply with, well, Newton's laws of motion are pretty much perfect. There's no exception to them. So if there is an action, there must be a reaction. If body A acts on body B will always act on body A. But the correct answer here is that the earth is attracted to the pen. Now, the other two statements are true, but they don't answer the question. And this is something that can often cause problems in physics in exam papers, where students say, okay, I've got something to say here, and I know I'm right. They write it down, they're happy with themselves, but they don't get their 3 or 6 or 9 marks, because what they're saying is true, but not answering the question. What is the reaction? Well, body A pulls body B. The reaction is always that body B pulls body A. So if the pen is pulled towards the earth, the reaction has to be that the earth is pulled towards the pen. Now, if you let go, will the pen fall to the earth? Absolutely it will, but that's not the reaction. That's actually pretty much the action. Will the pen bounce off the earth? Absolutely. And then, of course, when it hits the earth hits back. That's action and reaction, but that comes later. The pen is attracted to the earth even if you don't let go. So the pen is pulled towards the earth, and the reaction, the earth is pulled up towards the pen. Now, of course, how big is this force? A pen is typically about 50 grams or less. A marker is 50 grams, you know, a big board marker is 50 grams. So the force pulling that down to the earth is half of 1 Newton. But half of 1 Newton is enough to make a marker drop to the ground if you let go. Half of 1 Newton is nowhere near enough to lift the earth up towards the pen. So the force is there, but that doesn't mean it necessarily responds. If you push against whatever wall is nearest to you now, you probably won't push the wall over. The wall is too strong. The force you're creating is not big enough. That doesn't mean you're not pushing. The forces are there, even if other forces sort of stop it having an effect. And from Newton's third law, therefore, is where he got Newton's gravitational law. The pen is pulled towards the earth is pulled towards the pen. Forces always come in pairs, and that includes gravity. And this again was his big breakthrough in gravity, where he could put the maths on it. Other people had figured out that forces act in 2 directions, but they hadn't tied it in with gravity, and they certainly didn't come up with the gravitational formula that Newton left us with. Now, I'm going to leave that for a minute. I think I'll come back up again in a minute when we get to something on circular motion. I want to talk briefly about vectors and scalars, which also tend to tie in with equations of motion and so on. Both have vectors and scalars both are measurements, but vectors have magnitude and direction. Scalars only have magnitude. Typical vectors: force, velocity, acceleration. Scalars: something like mass, speed, distance, where even if an object has a speed, if we don't measure its direction, if we don't note its direction, then that's not part of its speed measurement. So that's a scalar. How these are put together, how this is asked at Leaving Cert physics tends to be pretty simple, and some textbooks they've dealt with stuff that is physics and could have come up, but it's not been the trend of the exam over the last 20 years. So don't worry too much. This is all about vectors in a straight line or right angle triangles, and that's pretty much the only thing that will come up for us. So if the vectors are in a straight line, if you push something along with two cooperating forces in the same direction, well, then it'll move as if you've added those forces together. If they're going in opposite directions, well, when vectors, not just forces, but when vectors are act in opposite directions, what we do is we subtract one from the other. So 15 minus 10 is 5 newtons, and that would push to the right. If two forces act at right angles to each other, one pushing across 3 newtons, one pushing down at 4 newtons, well, then it'll move at a diagonal. How big is the overall force that pushes it along that diagonal path? We can use geometry to figure it out. 3 squared plus 4 squared is 25, root 25 is Pythagoras' theorem. And it will move as if a 5 Newton force is pushing it along that line. We could figure out the exact angle from trigonometry, but that generally, I mean, that hasn't been asked in 15 years. It comes up in applied maths all the time, but not in physics at Leaving Cert. And similarly, if we're talking about vector resolution, where we have one vector, something like this, a guy pushing a big heavy box across the floor, but the box, he's pushing down at an angle. He's pushing down, if you can see my cursor, along this line here, but the box isn't moving along that line. The box, unless the floor collapses, is going to move horizontal to the floor. So what force actually pushes it along the floor? This is where you use triangles in the other way. So it's either two forces where at right angles to each other, and you just find the third side, or you're given a force and you take that to be the hypotenuse of the triangle and you just find the other two sides. So if there's 10 newtons there, we can resolve that or separate it out into two separate forces, one horizontal and one vertical. What size would they be? Just use trigonometry. So the sine of any angle is opposite over hypotenuse. So the sine of 30 here is FV, the vertical force over the hypotenuse is 10. And just rearrange that, you can find that the vertical force there is 5 newtons. The horizontal force, cosine is adjacent over hypotenuse. So cosine of 30 is FH over 10, and FH is 10 times cosine 30, which is 8.7 newtons. So if you push that wooden block, or a guy pushing the big box, whatever, across a horizontal surface, the force that actually moves it along that surface is not 10 newtons, but 8.7 newtons. And of course, that's why if people push very heavy boxes or pianos or cars, they tend to not push at an angle, but to get down so they can push straight in front of them so they can get full value for the effort they're making. The other force, the 5 newtons, hasn't disappeared. It's not making it move forward. It's actually making things more difficult, because it is essentially pushing it down, increasing friction, essentially making it heavier or appear heavier. Now, how does this come up in Leaving Cert? This is about the worst that you'd see. So a hurler strikes the sliotar with an initial velocity of 41 meters per second at an angle of 30 degrees to the horizontal. How far does the ball travel horizontally in 3 seconds? So in other words, like along the pitch, how far would it travel if you had to try to run underneath it to catch it? So it is always triangles. So the ball is traveling at this direction initially, 30 degrees, 41 meters per second. But we want to know, if you were running along underneath it, how fast would you have to run to stay underneath it so you'd be there to catch it when it fell, presumably. So it is always right angle triangles, and you're always looking for either the adjacent or the hypotenuse. So it's always either multiplied by cosine or sine. Now, draw a triangle to see which one it is. If you're unsure, do both of them and then just cross one out, which you could go with the one that looks most plausible to you. So cosine of 30 is adjacent over hypotenuse, VH over 41, horizontal velocity over 41. So that's 35.51 meters per second. And then how far does the ball travel horizontally? Well, this is where equations of motion always come up. So we're looking for the distance travel there. So in a way, it's s equals ut plus a half at squared, but there is no acceleration. So we're just left with s equals ut. 35.5 by 3 is 106.52 meters. Okay, so that's vectors, and I say vectors are an area that could be made infinitely more complex if they chose to do so, but that just has not been the focus of Leaving Cert physics for decades. So I just don't be paranoid about it. If you're doing applied maths, as I know many of you will be, or some of you will be, then you're good to go on much more complicated vector questions. But that's about the worst case that has come up in years in the physics. So as you're, if anything goes up with vectors, look at right angle triangles, draw the triangle, and try to figure it from there. It's pretty much, I don't want to say always, but in every example I can think of, you end up multiplying by sine or cosine. Now let's look at circular motion. Circular motion, simple harmonic motion comes up a lot, and I want to focus on those for the rest of our session. So there's many different ways that circular motion can be created. Fairground rides, turntables, gymnastics equipment. And they're all what's creating the circular motion in all of those are very different mechanical forces. There's probably a kerosene engine or something over here. That's obviously electric. This is whatever they're doing there. But there's certain maths that we can apply regardless of why something is traveling in a circle. For a start, we can always measure its speed in two separate ways. We can have what we call linear speed, the straightforward meters per second measurement, usually labeled as v, or we can talk about the angular speed, the angle it moves through every second, radians per second. And they're linked by the formula v equals r omega. Now, everything that is traveling in a circle must be accelerating. Velocity has a component of direction, speed and direction. So if it speeds up or slows down, we all know instinctively it accelerates, but also if it changes direction, it's changing its velocity and is therefore accelerating. So all of those objects are accelerating for very different reasons, but they all have what we call a centripetal acceleration, the acceleration of an object in circular motion, which is always towards the center of the circle. And we have formula, again, in the tables to allow us to calculate those. And following on from Newton's law, an object will continue in a state of rest or uniform velocity in a straight line, unless an unbalanced external force acts on it. So if it's not traveling in a straight line, there must be a force acting on it at all times, and that is known as the centripetal force, which links to the centripetal acceleration and is always towards the center of the circle. And again, we have formulae which allow us to calculate that. Now, let's have a look at how this might have come up in a Leaving Cert question. This one was from a few years back, 06. So first of all, definitions. Define velocity and angular velocity. Now, this is one that I often worried about back before this came up. I know a lot of junior cert textbooks will tell you that velocity is speed in a given direction. And that's like a perfectly reasonable way of introducing the concept, but it's not technically true. The definition of velocity is rate of change of displacement. So basically speed is distance over time, velocity is displacement over time, displacement is the vector equivalent of distance. It's very technical, almost philosophical, but that's your technical definition of velocity, displacement over time or rate of change of displacement. And they didn't give marks for speed in a given direction. And then angular velocity, omega, is given by omega is equal to theta divided by t. It is a mathematical derivation definition, and the formula is the only real way of defining it. That's quite common. A lot of our definitions in physics are mathematical statements. And does that mean you can just give the formula? Often, but do both. Give a sentence, give a formula. If there's some little flaw or glitch in one, they'll usually look at the one that's correct. If you just give a formula without defining the terms, so if you said omega is theta over t, you'd get 3 marks, not 6. Why? Because you haven't told us what theta and t stand for. So easiest way of doing that is to either put it in a diagram or put it in a sentence. So derivations we saw in that previous question about bungee jump. We're going to come back to that question actually. And now we're looking at definitions. These are the easiest ways of adding to your mark, of gaining marks in this exam. And most students drop marks on definitions and derivations, even though they do well elsewhere. And it's you know, it can often be what separates a H1 into a H2. Not the difficult, challenging questions that really require imagination and skill, something simple. A derive relationship. So here it's the derivation of V equals R omega. That's what it looks like. I won't explain the whole thing, all in the notes, all in your textbook, but that'd be worth 3 or probably this year more like 4%. And then use those formulae. So remember, like if it's a mathematical question, in physics, that means you're subbing into a formula. So if this is going around in a circle, what is the velocity? Well, turn to your tables. If no formula springs to mind, turn to your tables. And they've already introduced the formula V equals R omega in this question. So like I'm saying before, look for the clues earlier on. If we've already been looking at that formula, that's likely to be where the answer lies now. So 0.7 by 10 or by omega is 7 meters per second. And how long does it take to complete one revolution? That's what we call the period of a motion. Any motion that repeats itself all the time, whether it's a wave, simple motion, circular motion, has a period, which is 2 pi over omega or 0.63 seconds. That's junior cert algebra, subbing into a formula with 2 numbers that you're given. The whole trick here is to just be aware that there is a formula and to, you know, write it down. And, you know, if you got 2 or 3 formulas in mind, write them all down. Have a look to see which one works, cross out whatever you don't like the look of, but don't try to do it all in your head, do it on paper. Draw a diagram to show the forces acting on, I'm blocking myself here. Draw a diagram to show the forces acting on the ball when it's at position A. Now, this is an important one, there's an important point here. Clearly the ball has a weight. And strictly speaking, the name of that force is weight, not gravity. Gravity creates weight. His or her hand is holding that up. That's what we call the normal reaction. The ball is pushing down your hand is pushing back on that, Newton's third law. But crucially, there is also the centripetal force. How do we know it's there? Because you've been told it's acting in a circle. And if something is moving in a circle, there is always a centripetal force, a force pushing towards the center of the circle. Now, the student releases the ball when it is 130 centimeters above the ground. Calculate the maximum height and the time taken for the ball to hit the ground after its release. So, like I said before, don't look for the obscure patterns, look for the obvious ones. What comes up every year? Well, once it's released from the circle, it's no longer traveling in a circle, so it reverts to linear motion. Equations of motion. We're looking at UVAST, U, V, A, S, and T. Always a good idea to list what you know. It's traveling at 7 meters per second. We just found that. At the height of its motion, it will have stopped moving briefly for a moment in time. 0 meters per second there. The acceleration due to gravity here is operating in the opposite direction to the movement of the ball. So that's minus 9.8. And we're looking for the height that it travels up before it stops moving. So again, same equation as we saw before, but there's only 3 of them, so there's often a lot of repetition. Sub in, rearranging, you find that it travels 2.5 meters up before stopping. The maximum height, therefore, is 3.8 meters. A typical thing that a lot of students drop marks on at the time, they got 2.5 and they left it. Easy mistake to make, easy thing to overlook, to forget about the 130, the 1.3 meters. How can you avoid doing that? By drawing diagrams. Diagrams. If you're stuck, if you're confused, or even if you're not, draw a diagram to keep your own thinking clear and to explain the work you're doing to whoever is correcting it. How long did it take? Well, another equations of motion question. I'll skip across that one. Just that's the S equals UT plus a half AT squared. You get 1.59 seconds to hit the ground. Now, I want to go to another report. So there was 26 marks available for the maths in that question. So just going back to all of those sections, just to remind you what we've looked at. This is question 06. So we had the V equals R omega, get to 7 meters per second. How long, what speed is it moving at? What's its period? What's the maximum height above the ground? And the time taken for the ball to hit the ground after its release. So from all of those different sections, there was 26 marks, I think. How many do you think you could have got? Yeah, 26 marks were available for that question. How many could you have got by just writing down formulae?
Just a reminder as well, Tom, we have a few questions in here as well, if you have time to answer them at the end.
Sure, yeah. Okay, what do you have? Most people have answered. Give it another 5 seconds. Just throw in an answer. Say just commit yourself. So you're thinking about it. Okay, we'll leave it there. So we have 9 was the most popular answer there. 3. So 6 people thought 3 marks. 11 thought 6. And you know, if I was not used to looking at these marking schemes, I would have said 6. Like 26 marks. 6, you know, it's a decent chunk. It's quarter marks for just writing down the formula. They're given to you in the tables, for God's sake. Like, how many marks do you expect to get for that? But in fact, the answer was 12. Like 6 seems fair, 9 seems generous. 12, you know, if I'm being a purist, is it not a bit overly generous? Let's have a look at how that was marked. So, you know, there's a lot here. I'm not asking you to read the whole thing, but just look, that's the first 2 parts, the 7 meters per second and the 0.63. There was 9 marks going there, and 6 of them went for the formula. You know, whether you're obviously writing out the formula, if you've calculated it correctly, they're going to assume you had the right formula, even if you didn't write it down, but you should write it down. But if all you did was flick through tables and scribble down any formula you could see, even if you write down an extra 1 or 2, if the right formula is there, you should get the marks, unless they totally believe you that you're just, you know, gone to an extreme and you're just copying out the whole tables. So like always write down a formula. Before you move on from a mathematical question, you always scribble down a formula. If that's all you can do, that could be enough to pick you up 3-6 marks. In the second part, for 17, the V squared equals U squared plus 2AS alone got you 3 marks, and the S equals UT plus a half AT squared got you 3 marks. And there's alternative ways, and if you use V equals U plus AT, which you could have done there, you would also have got the 3 marks for that. So 12 out of 26 marks, close to half of all the marks went for the bit that didn't involve any real skill or intuition or in understanding. It just went for honoring the process by which physics is done. And really, it is appropriate when you think about it like that. This is how we always do physics. We find a formula, we sub in, and we find out what information it gives us and see if that's enough. If you're like working as a professional research scientist, sometimes you have to invent your own formula, and that makes it a bit more challenging, but it's still the process. So it's perfectly appropriate that the Leaving Cert respects that, but you need to be aware of that to work it in the exam. Now we'll do a little bit on simple harmonic motion, and then we will take a few questions before we finish up. So any motion that is repeated over and over again is likely to be simple harmonic motion. But to be simple harmonic motion, it must follow this formula: acceleration proportional to displacement from its equilibrium position. And that relates back to, it ties in with circular motion. There is a connection, don't have time to go through it here, but the omega is used for the period of either is 2 pi over omega, and the acceleration is omega squared s. So that's the same omega, even though for the simple harmonic motion, it's essentially just a mathematical link between acceleration and displacement. So we looked at that question on the bungee jump at the beginning, we've already looked at those parts, conservation of energy, the derivation. Remember, all those marks are there for the taking, the kinetic energy, and then it gets into the simple harmonic motion questions. So we got Hooke's law. So state Hooke's law, know your definitions. Restoring force in a spring is proportional to the extension of the spring. Simple harmonic motion. So again, like the conservation of energy, the definitions are straightforward. That would be either 9 or 12 marks usually. And then a little bit of maths. And this can often be a bit that intimidates people, but it's a relatively small part of the question. So calculate the length the cord would have if Henry was suspended at rest. Okay, so we know from earlier on in the question that Henry is 60 kilos. He's pulled down by gravity, 9.8. The elastic constant value of K is 250. And S is the displacement, so 2.352 meters is the extension on the spring or the bungee cord created by Henry. But of course, the cord was already 32 meters long, so 34.35 meters. And then calculate his maximum acceleration and his period of oscillation. Now, we don't have time to look at these in detail. The main reason I just want to stress them is that simple harmonic motion, like there's loads of subtleties and difficulties in this. But simple harmonic motion, like it's a mathematical concept. So it is always about formula. And as we've just seen, even if you get lost in the details, the formula will get you close to half the marks. But scribbling down the formula, like push it one step further and just try to sub in any way. And very often that will pull you up to like 9 out of 12 marks, even if you don't feel you're in a comfort zone. So here, linking together simple harmonic motion and Hooke's law, we can find that the K over M is equal to omega squared. Now that's something that's not in your tables, but features often enough that really it probably should be, so be aware of that. So omega squared is 4.17. We can then sub that in to get the acceleration is 5 meters per second squared, and the period 2 pi over omega 3.08. It's all about subbing into formula, so always start by writing down any formula that might be relevant. Draw a diagram to show the force is acting on Henry when he's at his lowest point. So weight is pulling him down and the restoring force of the spring is pulling him up. And if he's at his very lowest point, he's about to accelerate upwards. So the restoring force will be the larger. So how would you study for all of this? Well, I would start intense exam-based revision by looking at section A like we were talking about yesterday. When you get onto the mechanics, it's easy to find mechanics questions. It's pretty much question 6 and 12 part A every year. And like the more you do, the better. That's the suggested list of questions that we're going to share later in the week. But it is, I say, for mechanics alone, it's very easy to find the questions. Question 1, question 6 and 12 part A. Okay, Fionn, how are we doing? What sort of questions do we have?
Yeah, so I have a few for you here. So I have one. Would you mind asking what is displacement?
Displacement is the vector equivalent of distance. So it's one of those things, it's so philosophical, but not worth worrying about. Like if I'm looking across the room right now and there's a wall about 3 meters from me. So the distance, the wall is 3 meters from me. Displacement, it's 3 meters north. Displacement is distance factoring in length.
And we got one at the start of class actually. If we draw a graph where values are proportional, like for F equals MA, does it matter what value goes on the X and Y axis?
That's more likely to feature in section A than section B, but it's a very good question. Strictly speaking, no. Like there's no law about this. If all you're trying to show is that 2 measurements are proportional, F and A, then a straight line graph through the origin proves that. So it doesn't matter whether that's, you know, F on the y-axis or F on the x-axis. So if all you're trying to show is that it's a straight line graph, that 2 things are proportional, it doesn't matter what's on either axis. But very often we have a follow-on calculation we're likely to do. So if you're trying to show force proportional to acceleration, it doesn't matter what goes on the y-axis. But if you put F on the y-axis, the slope of that line will equal the mass of the system, which is something you're likely to be asked to do. So strictly speaking, the answer is no, it doesn't matter. But practically, for exam purposes, what I would do is just practice it with one way in mind. If you've looked at past questions, just, whatever's come up in the past is likely to come up again, just to be ready for things like that. Basically, if you used a slope, it's better to have it pre-planned. Anything else?
Yeah, we have just two more. When dealing with equations, would you rearrange equations, getting what you want on one side and then input values, or vice versa?
Whatever you like to do. Personally, I like to rearrange subject or formula, sort of, and that's the way you learned it at junior cert. I prefer to do that first and then to sub in. But over the years, I've noticed that a lot of people, including very experienced people, would prefer to put the numbers in first and then rearrange it. And it just doesn't matter. Mathematically, in terms of, even from a purist perspective, both are 100% valid. So the thing to do is do it the way that you're comfortable with. Trust your own algebra skills. And the more you trust them, the more you can develop them to get more and more comfortable. But everybody has their own way of thinking their way through algebra questions, often based on whatever teachers you've had in the past. But some of you will have had, 4 or 5 or 6 different maths teachers over the years, and you'll have been shown slight variations. So never feel it must be done in a particular order. Do it the way that you understand. And in particular, it doesn't matter whether you sub in first or not. That's one of those things I'd say it splits about half and half. So there really is no preferred method there.
Cool. And we have one final one. Is the circular motion equations in the formula book?
Yeah, I have a set of tables beside me. Where are they? It's labeled funnily, it's motion in a circle rather than circular motion, something like that. Motion in a circle, it's on the bottom of page 51. But one little thing, and this is why it's really good to work from tables rather than textbooks as you're preparing for the exam. All of the equations that I looked at there today are on the bottom of page 51, apart from the period of circular motion, which is linked in with simple harmonic motion on page 54 instead, t equals 2 pi over omega. So it's the sort of stuff that if you were using the tables for the first time in the exam,